scientific / policy talks. There'll be one in the now and one in the afternoon on exciting areas of physics. And our first speaker is David Reitze, who is a distinguished laser physicist at the University of Florida and Caltech, and has been for many years the spokesperson, now the director of LIGO. And as you all know, LIGO 4 years ago announced the first direct observation of gravitational waves as well as black hole mergers, and has launched a new window to the universe with enormously exciting physics, astrophysics, cosmology. LIGO is a large-scale international collaboration involving over 1,000 scientists in many countries, and David is in a good position to both describe the exciting new physics as well as the challenges of putting together such an international collaboration in today's world. The title of his talk is Detecting Gravitational Waves, the Role of International Collaborations. David.
All right. Oops. All right, getting a PowerPoint presentation is about as complicated as detecting gravitational waves. View. Slideshow, there we go. Okay, so let me get started. First, thank you for inviting me to this conference. I guess this is sort of a case study of what Steve Chu talked about earlier, and I'm going to talk specifically about gravitational waves and the role that international collaboration plays, and it's a critical role. We couldn't do this without international participation. But I'm going to start, since this is the American Physical Society, by talking a little bit about the science to sort of motivate you about why we need these large collaborations. About 4.5 years ago, we discovered a momentous event. We discovered two black holes that were orbiting around one another, merging. And I show this slide because I think the data is really, let me see if I can get that out of the way. The data is quite remarkable. So these were the gravitational waves that were recorded, red from one of our detectors in Hanford, Washington, blue from the other detector. There are amazing things in this data. First of all, that the data actually tells you what you looked at. So in that waveform, which is kind of gnarly, there are information encoded about the nature of the event. And in this case, it was two black holes merging together. And you can actually take the data from the waveform, feed it back into Einstein's field equations for general relativity, and if I can get this going, you can actually, oops, looks like things have locked up here. Let's see if I can, oh, I see what the problem is. No, it's trying to find a Wi-Fi network. All right, so now let's see if it works. No, still not. There we go. Okay. What you're looking at is actually a simulation that's done on a computer, which shows these two supermassive, well, not supermassive in the galactic sense, but supermassive in the stellar sense, colliding together and producing this burst of gravitational waves. Many amazing things about this. First was that it's the first detection of direct detection and measurement of gravitational waves. Second, it's really the first time that we've ever seen two black holes orbiting and merging for one another. So this sort of gives you a taste or a motivation of why this field is really, really fundamentally important. Everything we know about the universe, we know from, and I'm talking about the large-scale universe here, we know from the tools that have been developed over hundreds of years. So telescopes going back to the era of Galileo collect photons. Photons look at certain classes of physical events that tell us about astrophysical objects, astronomical objects. There, of course, are neutrinos and also cosmic rays. that come out of nuclear collisions and decay processes, and then there's also the subatomic physics. So gravitational waves are fundamentally different from all of these things. They're produced really by relativistic masses, and to detect them, you really need astrophysical sources, and they need to be violent and relativistic. They're pure information carriers because they travel through everything. Right now, you're being bathed with gravitational waves from the moon moving around the Earth. Don't worry, the amplitudes are small. They're not doing anything to you. And they propagate with an amplitude that's a bit different from what you expect in E&M. They fall off as 1 over r, and that's actually 1 over distance, and that's actually very important. The 2016 review of the ASTRO 2010 Decadal Survey put it this way, and I'll read it for you. I think this really puts a point on how important this discovery was. The most dramatic astronomical development of the century thus far has been the detection of gravitational waves from merging black holes during the first science run of advanced LIGO. All right, so let me talk a little bit about the future. I'm going to come back to another scientific result at the end, but I'm going to sort of try and get people focused on sort of the big picture questions. So there are a number of really fundamental questions that gravitational waves can either directly answer or at least shed some light on that gets us closer to understanding truly how our universe works. So one fundamental question in physics is where does general relativity break down? Gravitational waves probe gravity in its strongest and most dynamical regions. So we might get some hints from gravitational waves. What are the fundamental nature of black holes? Another prediction of general relativity, bared out by astronomical observations in the X-ray and now by our LIGO discoveries. They turn out to be quite simple in Einstein's theory. They consist of basically their space-time, but they're measured by, you can quantify the curvature of space-time by a mass and also by a spin or angular momentum. But maybe they're not that simple, and the information encoded on the gravitational waves can tell you that. Turning to a different class of sources, binary neutron stars, when they collide, you actually get a remarkable series of events that happen. They produce light across the electromagnetic spectrum, and the neutron stars are these big sort of stellar-sized atomic nuclei that when they collide at significant fractions of the speed of light. And there's a lot of information encoded in that, and you can study matter in the extreme. There's also nucleosynthesis that comes directly out of that also. One of the fundamental questions is where do the heaviest elements in the periodic table come from? So you can go from physics to astrophysics, and that's what I really like about gravitational waves is it touches on a lot of different kinds of disciplines. So if I were giving this talk 3 years ago, the question I would have asked you is, do binary neutron star collisions produce short, hard gamma rays? And the answer we now know, because we've observed one of these events happening, is yes, they do. So that's gravitational wave data on the bottom, X-ray data and gamma ray data in the top 3 panels there. And what we saw was a coincident emission of a gamma ray about 2 seconds after the gravitational wave. So now the question becomes, so how does that happen? And more of these observations will tell us that. How do massive stars explode? We know most of the physics of supernova, but we don't know all of it. In particular, we don't know what restores basically the final explosion after the collapse. How and where are binary black hole systems formed? This is a fundamental question that a lot of astrophysicists would like to know because in some sense it's the end stage of stellar evolution. We know there are stellar mass black holes. They've been detected by X-rays and now by LIGO and Virgo over the last 40 years. We know that supermassive black holes exist in our galaxies and in most of the galaxies in the universe. But what's between them? Are there intermediate mass black holes? How do these supermassive black holes come to form? And the really interesting question is, because we're using a new tool and opening this new window, there may be other things out there that we just don't know. Finally, I'll turn to cosmology and just go through a couple of these things because I think they're quite interesting. First of all, can we detect primordial gravitational waves? If we could actually see back to the moments of basically the Big Bang, which is something that electromagnetic astronomy cannot do for us. Can we measure the Hubble constant? The answer is yes, and that data that we show there actually is quite interesting because it shows that our measurements, which admittedly have much larger error bars than the measurements that are done by either looking at the cosmic microwave background or supernova explosions, actually come up with about the same number. But there's a tension in those other measurements, and gravitational waves, after we make multiple detections, might be able to actually resolve that tension and show where why that tension exists. Finally, and this is somewhat more speculative, but can we find clues to the nature of dark matter and dark energy? If dark matter gravitates the way normal matter gravitates, there might be some interesting things we can learn from that. Okay, so what are gravitational waves? I've told you why they're important. I think most people in the audience know what they are, but it's always nice to be told something that you already know. So they are ripples in space-time. They're really fluctuations in the curvature of space that are produced by accelerating objects, any accelerating objects. And in this case, this is a cartoon, so it's not physically totally accurate, but as these objects are orbiting around, and in this case, let's pretend they're black holes, they're orbiting around at about half the speed of light as they get very, very close to one another. They're producing significantly more amplitudes at significantly higher frequencies, and they're propagating outward. All right. So, and what's left behind, of course, is a bigger black hole. There's a huge amount of energy released in that process, by the way. For the first discovery, the data that I showed you before, there's about 3 solar masses released in a fraction of a second. So these are very, very luminous events in that sense of the word. Now, the challenge is to measure these things. So what they really are strains. They're changes in length per unit length. So if a gravitational wave were coming at you, you would be standing, you would get sort of a little bit thicker and a little bit shorter on one half cycle, then you'd get a little bit taller and a little bit thinner on the other half cycle. So it stretches and compresses literally space itself. So the metric, if you will, is changing for the experts in the audience. So you're trying to measure a displacement over a baseline or a distance L. And the challenge for us is that for these sources of interest, this delta L over L is awfully tiny. It's 10 to the minus 21 to 10 to the minus 24, all right, which immediately suggests that you need to actually think hard about how you're going to do these kinds of experiments. And so now let me turn to the LIGO observatories. These are the NSF-funded LIGO observatories. This is one of our observatories in Livingston, Louisiana. And it's an interferometer. I'll say more about interferometers in the next few slides. But if you look at this, I purposely put those errors there to show you what L is in this case. So the L that we're measuring over is about 4 kilometers. And I'll go more into the interferometer in a minute. Here is an exact clone, almost an exact clone of the Livingston interferometer. It happens to be in Hanford, Washington, about 3,000 kilometers away. Again, 4 kilometers here. So what are we trying to actually measure? How do we measure gravitational waves? Well, this is a simple cartoon, but hopefully it'll get the idea across for you. We start with a laser, a very stabilized laser. I'm color coding the wavelengths here just to show you can see interference. They go out 4 kilometers. They come back. The laser light recombines. The path length differences between that beam splitter in the center and the mirrors are set such that none of the light goes out to that, what we call the dark port. But as a gravitational wave passes, it differentially stretches and squeezes the interferometer or the lengths of the interferometer arms, and basically produces a modulated light signal, which you pick up with a standard photodiode like you would use in your DVD or Blu-ray player or something like that. To put a point on this, this is a nice cartoon, but it overestimates the stretching and compressing in our interferometer by about 1 trillion. All right, so we're actually measuring displacements, that's the delta L, to about 10 to the minus 18 meters. So it's a tiny, tiny fraction, maybe 1/1000th the diameter of a nucleus of an atom. So there's a tremendous amount of work that one has to do and that a group of people, a collaboration, has to do to be able to achieve this kind of measurement precision. So how does it really work? So a gravitational wave detector, an interferometer, is really a transducer. It basically detects stretching space-time by measuring the basically difference in the light travel time along the two arms of the interferometer and turns that into a modulated signal. So at the end, we record photocurrent. And I'm just going to walk through some of the key technologies here. So this is a little more sophisticated view of the interferometer. It's still actually quite simplistic when you actually compare it to the real thing. But we start with a very stable laser, and this laser is the most stable laser in the world, to my knowledge. And we then have to, because these interferometers are on the ground, we then have to be able to keep all of the environmental disturbances away from them. The ground is shaking quite dramatically at low frequencies, and what we need to do is roll that off to our frequency band, which starts at about 10 hertz or so. So we have actively controlled seismic isolation. We then have quadruple four-stage mirror suspensions that actually, basically, this is where the interferometer beams go through in those arms of the tear. They're called test masses. They are actually what responds, in some sense, to the fluctuations due to the passing gravitational waves. And then finally, there are the mirrors, and this is where, in some sense, the rubber hits the road. These are some of the world's most precisely figured mirrors and coded mirrors. And again, there's a lot of technology that goes into all of this. I should point out also, I don't show it, but we actually have recently implemented a technique that we borrowed from quantum optics, something that's been known for about 35 years, called squeezing. So we actually inject quantum engineered states that actually, in one quadrature, beat the Heisenberg uncertainty principle, and that allows us even more sensitivity. So now I want to transition to what it takes to make all that happen. So there's a large ecosystem that one has to establish and grow and nurture over a large period of time with a large group of very different kinds of expertise to be able to pull this off. So one take-home message from here is gravitational wave science is really, it's big science. It's not quite on the scale of, say, CERN, LHC, particle physics, but it's very, very close. And I don't know if you could read this. It was hard to fit all this into one slide, but in order to do gravitational wave science, you have different sort of dominant things that you need to do. You need to design and operate gravitational wave interferometers, like I just showed you. You then need to get the data out of those interferometers. All right, you need to store it, you need to archive it, you need to process it. You then need to have codes and people who actually know how to search the data for gravitational wave signals, all right, and there's a number of things that go into that. Then once you've found the gravitational wave, you have to extract the information from the gravitational wave. Are these black holes? Are they neutron stars? How far away are they? Where are they? Are the neutron stars spinning? Are the black holes spinning? And then there's another part of this that's actually very, very important, which is thinking ahead, all right, having future R&D programs to be able to constantly improve our detectors, because as we improve our detectors, we can see further and further out into the universe. And finally, something that, if you work in a laboratory, as sort of a single investigator in small collaborations, you might not think of as much as you have to in a big collaboration, but I would call the sort of collaboration infrastructure. You have to have all of these people, maybe not talking to all of each other, but you have to have them able to communicate. You have to be able to have them get together, organize meetings and things like that. And these are, with large-scale collaborations, these are quite challenging. And just to put a point on the breadth of expertise that we have here, and I haven't used the word engineering yet, I don't think in this, but the engineers that work on LIGO are critically important. On the one side, we have the vacuum system, all right? These 4-kilometer arms, all right, are basically tubes that are about 1.2 meters in diameter, and there's a 10 to the minus 9 torr vacuum system in there, and it's extremely clean. It has to be extremely clean. So you've got those people. You've also got people that have to develop control loops for basically using low noise, analog and digital techniques to be able to sense and control the interferometer. So they're a different group of people. Then you have to have people who know how to do the searches. So for example, we have a whole group of people in the collaboration that do nothing or mostly do waveform development. So they actually calculate what kinds of gravitational wave forms we would get from binary neutron star collisions or black hole collisions as a function of the masses, as a function of the spins. There we use numerical relativity to do that. So on the one hand, you've got vacuum technologists. On the other hand, you've got people that work in lasers and optics, and actually that's a big part of what we do. And then you've got numerical relativists. So there's a huge breadth of expertise that's needed to tie this all together. So now let me talk about the collaboration, the LIGO scientific collaboration, because I think in order for this to happen, in order for us to have produced these results, we had to have a head start. The history of LIGO goes back really 40, maybe even longer than that, 40 years, maybe even longer than that. LIGO has a very complicated history. In the end, it worked out. It was high risk, but also deemed to be high reward science. The collaboration was founded in 1997, so a little over 20 years ago, with approximately 250 members. Right? Now, the charter of the collaboration, all right, is very short. It's 2 pages, but it's encapsulated in this statement right here. The LSC is a self-governing collaboration seeking to detect gravitational waves, use them to explore the fundamental physics of gravity, and develop gravitational wave observations as a tool of astronomical discovery. All right, there's more that comes after, but that's basically it. All right, and it was formed as a self-governing collaboration, internationally built into it. So of those 250 members, I roughly estimated that 40% of them were from outside the United States. And another key point here is there was essentially no barrier to entry. So to get into the LIGO scientific collaboration, you didn't need to bring a dowry. You didn't need to bring funding from your agencies. You just needed to sign up to the mission, which is there. And so because the barrier for entry was very low, we were able to grow the collaboration and pull in the expertise that we needed to do all those things that I showed you on the last slide. So here's the LSC today. It's over 1,300 members. There are 118 institutions, the last time I counted, from 19 countries. We always show our logo chart, so chances are if you look carefully, many of you in this room will see your institution on here. So there's Stanford, I see, there's Berkeley, there's Caltech, international institutions also. But perhaps more importantly is this. This is the geographic distribution of the LSC. So a lot of groups and institutions in the US, but about half of the LSC members actually come from outside the US. And again, this growth has happened somewhat organically, somewhat in a planned fashion, but heavy concentration in Europe, Russia, India now, within the last few years has really developed a community of gravitational wave physicists, Japan. We do have a group in China. It's one group, and it's not a big part of our collaboration. So we don't have the same kinds of issues that were addressed in the last talk as much as maybe other collaborations do. Australia is a big player, and a couple of groups in South America. So this is really quite important. The other thing I'll emphasize about our collaborations is we look at demographics from time to time, and it's a really, in terms of age demographics, you look at this slide and you get very heartened by it because over 50% of the collaboration is either graduate students or postdoctoral scholars, and we even have undergraduates that are part of our collaboration. So because I think the science is so new and exciting, we're actually drawing new people. And again, these people come, some of them have expertise in quantum optics, some of them have expertise in astrophysics, some of them have expertise in general relativity, so they all find an important role to play. Okay, so I'm going to list just a few of what I would call the critical roles that were played by our international collaborators. And the first one I'll talk about is that the detector that I showed you, the Advanced LIGO detector, there were key collaborations and key contributions from a number of groups, mostly in Europe. So the laser that I showed you came from the Max Planck Institute in Albert Einstein, the Albert Einstein Institute in Hanover, Germany. Those suspensions, which are really a key part of making LIGO work, were provided by the University of Glasgow. The optics, some of the optics at the end of the interferometer were provided by ANU. The mirror coatings were provided by a company in France, but it's an interesting company that actually is supported by the government, so they have an R&D program. Even something as sort of boring as Faraday isolators were actually needed to be developed. We couldn't buy them off the shelf, and those came from Russia. So these were all in-kind contributions, but not just the in-kind contribution, but the expertise that went into designing all this stuff also. There's a prototype interferometer in Hanover, Germany that tested, not everything, but quite a bit of the technologies that we use now. Computing is a big deal for us. We actually do a lot of computing. We have, I don't know, by my last count, probably 10 or 12,000, access to 10 or 12,000 nodes that are actually in-house. In other words, we in the collaboration control them. 30% come from overseas. International groups, all right, are leading many of the science searches in the LSC, and that's something that's very, very important. And they occupy many of the leadership roles. And I could go on and on and on here. One thing that I'll say that I think is worth emphasizing is we have a culture of, or we try to instill a culture of openness. So particularly with a detector. So if you go and you want to learn more about the advanced LIGO detector, everything that we have done is public. You can go to we have a document center that you can go to, and if you're willing to do a little searching and sift through thousands and thousands of documents, you can get the designs to the last nut and bolt of that detector. And that openness actually is very important for us because it allows us actually to avoid some of the problems that you have with proprietary information or IP. Many of you may know something about export compliance. So by being open, we take advantage of something known as the fundamental research exclusion, which basically allows us to have conversations with anybody almost anybody, because of the fact that everything that we talk about is open. Okay, so one of the themes that I'm going to point out, or that I want to emphasize here, is cooperation over competition. So many of us, maybe all of us in the room, are physicists or scientists, and we know that science is competitive and that scientists are competitive. In my experience, not all the time, but mostly in a very collegial and friendly manner. There's cooperation, if you will. It's cooperation and competition. All right, but this is not the way science is done. And if you think about high energy experiments, you think about the LHC, you have CMS and you have ATLAS, all right, and they're competing experiments, all right? We do not work in that manner, and the reason is because the science drives us not to work in that manner. The key scientific motivation for cooperation is that by having more detectors, and I've already showed you the 2 LIGO detectors, you get more and better information. It increases the confidence that you're actually making a detection. You get more precise extraction of the underlying physical event that produced the gravitational wave, because we can measure, for example, polarizations if we have detectors in different parts of the world. And perhaps the most important, and I'll emphasize this in a few minutes, is that we get higher precision and accuracy in localizing gravitational wave sources. One interferometer, it's not really too hard to think about this if you think about how gravitational waves interact with interferometers, gives you almost no information about where a source came from, unlike a telescope, which is very good at localizing information. But the more interferometers you have, the better you can actually do that localization. And this is very powerful because it allows us to take gravitational wave data, combine it with data from observations from astronomical telescopes, gamma ray telescopes, optical, radio, what have you, all right, and get a lot more information about the event. So the scientific payoff really drives you to try and overcome the barriers to collaboration. And we realized this very early on. This was realized by a number of the leaders in the field, for example, Reitze and Barry Barish in the late 90s and early 2000s. But it took a while to actually develop agreements. So We have an observatory that's operating in Italy. It's funded by Europeans, primarily by the French and Italian governments. It's called Virgo, very much like our LIGO interferometers, but it's a completely different detector designed by a completely different group of people who operate in a completely different collaboration. All right, and so we realized that by taking their data and our data and bringing it together, we could do this better science that I talked about earlier. And so we after years of negotiations, and really a year of very hard negotiations, we came together and signed an agreement in 2007. And I will read what that agreement says, because I think it sort of, again, frames how we think about gravitational wave science and the need for collaboration. We enter into this agreement in order to lay the groundwork for decades of worldwide collaboration. We intend to carry out the search for gravitational waves in a spirit of teamwork, not competition. Furthermore, we remain open to the participation of new partners whenever additional data can add to the scientific value of the search for gravitational waves. All partners in this collaborative search should have a fair share in the scientific governance of the collaborative work. So these are sort of I would call them our stone tablets that come down from on high to how we think about collaborations. And this collaboration has worked remarkably well. And there's some fortuitous in this, too, that the Virgo upgraded their detector and came online on August 1st, 2017. And 2 weeks later, made a key contribution, along with the LIGO detectors, in detecting a pair of neutron stars colliding, which I'll say more about again later. Fast forward 12 years. In Japan, they've been working on an interferometer, a really actually technologically advanced interferometer. It's underground. It uses cryogenics. And just last year, at the end of last year, that agreement that grew out of the LIGO-Virgo agreement is now the Virgo-Kagra-LIGO agreement. So Kagra is actually joining the team, if you will. And right now their detector isn't quite operating at the level that it needs to be, but it will. And so they'll make contributions very soon. And so if you sort of then say, okay, how big is our collaboration now, or this meta-collaboration? It's about 2,100 people. And I should point out here that this is not, when we talk about governance, each collaboration maintains its individual identity, has its own set of bylaws, has its own set of membership rules and authorship policy, although over the years we've had to sort of bring them more and more together. So what we have here is what I would call a collaboration of collaborations. And that has advantages and disadvantages. So let's talk about some of those challenges, okay? Challenges for doing big collaborations like this come in all shapes and sizes. So there's scientific and technical, of course. We have to be worrying about what's the best way forward to do the science and develop the technology. But then it gets into people. There's cultural, there's temporal, there's sociological, there's budgetary stresses and things like that. So let me give you a few examples of some of the things that we've had to wrestle with to make this work. First is data rights. Who in each collaboration has rights to the data? Our policies have evolved actually over the years to become, I think, more friendly to this. Who is authorship on papers? How much work do you really need to do to become one of the names, one of the hundreds and now maybe even 1,000 names on our publication papers? What technologies and what software packages to use? This is actually a very important question because scientists tend to be innovative and creative. They come up with their own ideas, they advance them, and they get to a point where you may have competing technologies for doing a certain part of the detector or a certain analysis. And so you have to choose because you don't have enough time and people to do them all. And so there are winners and losers in that process, and that can be somewhat frustrating at times. Since we don't have a global governance structure, we have to plan, coordinate, and negotiate on how we're going to do our joint observing runs, how we're going to upgrade, so that we make sure that all these interferometers are on the air at the same time. Anybody who's worked in a global collaboration before knows that time zones are the bane of our existence. If you're working with somebody in India, somebody in Europe, somebody in Asia, and somebody in the United States, if you want to have a telecon with all those people, someone's going to suffer. Someone's going to be getting up at 3 in the morning or going to bed at 11 o'clock at night. It's a logistical thing, but it's a really important one. Computing resources is another one. I've already talked a little bit about that. Publication review and approval processes. All right, this is very, very important. One of the things that we pride ourselves on is putting out the best publications that we can, and we do a tremendous amount of work to make sure that what comes out, we're confident is absolutely correct. And we don't always get it right, but we go very hard. And those reviews and approval processes sometimes lead to bottlenecks and friction. One that really hit home to me is allocation of credit. When you've got this many people working on a project, and those people come from all over the world, when you make a big discovery like the detection of gravitational waves, you worry about who's going to be on the stage announcing the detection, who's going to be giving credit in Europe, who's going to be crediting it. And it's very complicated, and people get upset if they don't think that they're getting the proper credit. And this has actually led to some tensions in the collaboration. And finally, one that's actually become more recent is what I call public data release. So we release our data to the broader research community, all right, which means they can look at our data too. Now, we have a latency period, all right, but they will eventually get it, and that creates this thing. Okay, my clock is working now, good. All right, so there are many challenges. I just gave you a list of the few. On any given day, if you ask me what the challenges are, I might give you a completely different list. But overcoming them really requires, I would say, focus, diligence, patience, understanding, self-sacrifice, that's actually a big one, and dogged persistence. I think the reason we have been successful and stayed together as a collaboration, as this meta-collaboration over the past 20 years, is that we all had focus in our eyes on the prize. Now that we've actually detected gravitational waves, there are starting to be some I would say, some external pressures and even some internal pressures that are going to force us to evolve a little bit. I will say the following thing, that there are people, and people are people. So you've got to trust people, and sometimes your trust is violated, and so robust conflict resolution processes are needed. And I can tell you, I've been involved in a number of those things. But I would think thus far, we've managed to make it work. And I will point out that there's a sociologist from Cardiff, Harry Collins, who's been following this field for over 40 years, I think goes back to the 70s. And he's written several books on the sociology of LIGO. So in some sense, and gravitational waves. So in some sense, we are the apes, and he is Jane Goodall. And you can read his books. They're very readable. They're about sociology. All right. So let me now come to what I would call the next level of collaboration. All right. When Virgo joined, nature was just very kind, and we were very lucky. Virgo had just turned on, and we saw a gravitational wave event that was registered in our detectors. All right, each of our detectors, but with different time delays. And as I said before, by having multiple detectors, you can get precision, kind of precise, not so much in the astronomical sense, information about where the source came from. We had realized this, and as a collaboration, we had taken a lot of time to establish agreements with astronomers who study time domain, high energy events. And this was, again, a very complicated negotiation because you're dealing with a lot of different people and a lot of a culture that's quite different. The culture that I'm describing is really more a high energy culture, whereas the astronomers tend to be, at least in my experience, very, very much sort of on their own and competing with one another. So we spent a lot of time in 2015 and 2016 setting up what we call a private network. You could get our data, you could get our alerts. We would tell you where we see these signals, provided you sign an agreement with us saying that we could publish together. We don't want you to publish your stuff before we publish our stuff. Of course, at the same time is fine. This really paid off because on August 17th, we detected an event. It was also detected, I showed you the data before, actually early in the talk, by the Fermi Gamma Ray Telescope. All right, and what we saw was the collision of two neutron stars. So this is a movie that really sort of illustrates how dramatic this is. So these are stellar mass, 1.5 solar masses, orbiting together, the orbit's decaying, wham, they come together and they release all kinds of stuff. First of all, nuclear-rich material comes out. There's gamma ray burst that comes out, light across the electromagnetic spectrum, and following the evolution of the optical, and the gamma rays are quick, they're over quickly, but following the evolution of the optical and the radio really gives you a lot of information, even the X-rays gives you a lot of information about this particular source. And this was a gold mine event, and I can say that literally because this event actually, astronomers, basically the time domain astronomers, were able to actually show that this is one of the regions where you would get synthesis of higher elements gold. So this sort of puts a point on why you want these multiple detectors. This is a map showing the localization of the event using the gamma ray, Fermi, and integral, using the 2 LIGO detectors alone, and what happens when you bring Virgo in. And that sort of that oval up there is about 30 degrees, square degrees. And astronomers very quickly, after learning that they saw gamma rays with this event, started looking at everything in that field of view, all the galaxies, and they zoomed in, and 11 hours later, they zoomed in on this galaxy. This is NGC 4993. It's about 40 megaparsecs, so 140 million light years away. And what they found, and this is a picture from the optical, this is from the SWOPE telescope, that circled dot is the resulting event, basically was produced by the collision of that. In this case, it was probably a black hole with a lot of basically material accreting light around it. So it was a remarkable discovery. As I said, one of the questions one can ask is where do heavy elements come from? From that one event alone, we learned that binary neutron stars are everything there that's in yellow in the periodic table is produced in binary neutron stars, not collisions. Now, it may not be the only source of production, but it's certainly a large source of production. So that's quite exciting. So why is this a big deal? This is a big deal because it wasn't just the 3 gravitational wave observatories that were operating. It was 75 astronomical observatories, including 7 in space, right, NASA telescopes, and also including the NSF Ice Cube detector. We wrote a paper about that. We wrote lots of papers about this, but this is the paper that I like to actually quote. It's called Multi-Messenger Observations of a Binary Neutron Star Merger. And that list is not a list of people. It's a list of all of the groups and collaborations that were involved. See End Matter for a full list of authors. There were 3,500 authors on this paper, over 950 institutional affiliations. Just managing the author list and affiliation list was quite complicated from an accounting standpoint. Many of these people had never worked with one another before, and this paper was written in 2 months, so it was quite exciting. Now, I should point out that LIGO is high risk and high reward science, and it came with some controversy. So it's easy to think about where we are now and say that, oh, this was a brilliant investment, but it's a little more complicated than that. LIGO almost didn't make it. There were a number of very prominent astronomers and other physicists who thought that this was quite crazy. How do you measure something 10 to the minus 18 meters? All right. These are excerpts from the congressional testimony to the House Science Subcommittee in 1991. The sources we think we know out there are too weak to be detected in gravity waves by LIGO. LIGO is at best a physics experiment, not an astronomical observatory. Astronomers can think of cheaper experiments that are much more likely to yield fundamental advances. And even if all the estimated improvements over the LIGO prototype, and that in this case is the 40-meter prototype at Caltech, are achieved in LIGO, the resulting sensitivity of LIGO falls at least 10 times short of being useful astronomically. These criticisms are all valid. All right, they were all valid. But again, why this worked was because there were some visionaries at the National Science Foundation who supported this. There's a great article. Dennis Overby's done a number of articles about gravitational waves and LIGO. This one I really like. It came out earlier. Future Nobel Prizes are won in congressional committee hearing rooms and on august panels of the National Academy of Science by budget-wielding bureaucrats. Without their efforts, there would be no labs or research grants. So I hope there are no budget-wielding bureaucrats in the audience right now. And I want to point out Rich Isaacson here, who was really the visionary who kept this alive within the National Science Foundation, and there's now an APS prize named after Rich. Looking forward, and in the time I have left, since I don't have much time, we're even going to do more. We've actually partnered with LIGO, and the National Science Foundation has partnered with India to actually build a clone of the 2 LIGO detectors that we have in the US and India. And we have the components in storage. We are basically going to collaborate with them to build this detector. This is a design for their detector in India. It looks much like our detector. This was codified in an MOU that was signed by the director of NSF, Franz Cordova, and her counterpart Dr. Basu in the DAE in 2016. And the project is moving along. And we've actually cleared a key milestone, which is getting the getting land in India. Let me almost finally talk about where we're going next. The way we operate now may not be the way we're operating in the future. So planning is underway for a new generation of interferometers. One in Europe is called the Einstein Telescope. The other in the United States is called Cosmic Explorer. That diagram there just gives you a sense of scale. That LIGO is 4 kilometers, Cosmic Explorer is 40 kilometers. These are concepts. I don't actually guarantee that any of these things will be built in any of the ways that they're pictured here. But we've been doing a lot of sort of thinking about how we're going to try and take the collaborations and the strengths we have now and actually extend them and move them forward. And a committee of something known as the Gravitational Wave International Committee has actually looked at this. And one of the things they looked at was governance. And I think this is important, recognizing current technical development efforts, but in view of the resource, technical, political, and scientific challenges, we recommend that unified global coordination towards developing and implementing a global 3G capacity. In other words, not just collaborations, but something more stronger, like, for example, a treaty-level organization, or ERIC. That would be hard for the US, but this is the kind of thing I think we're going to go. So I'm going to stop there, pointing out that we publish our stuff in PhysRev letters because we love PhysRev letters, and thank you for your attention.
David, that was a great talk, a great collaboration, and great science. We have time for a few questions. I want to ask you one myself, and that is, you are carrying out an experiment urged by the NSF and public release of data almost immediately.
Right.
When you announce a discovery, you make the data available to hungry astronomers and astrophysicists around the world.
Right.
How is that working, that experiment?
You said the right thing. This was not something that we stumbled on and came to ourselves. This was something that came down from the National Science Foundation. I think it even came from higher up, the National Science Board, and maybe even higher up than that. We developed a policy that we thought was quite sensible. Actually, somebody in this room, Beverly Berger, helped us when she was at NSF develop that. And it worked quite well because no one was interested in our data up until 2015. But what we're seeing now is that there's the policies that we have may be a little bit, I would say, behind the times in the sense that there's a balance that you have to strike. And the balance is, you collected the data, you're the collaboration that, I don't want to say owns the data, but that took the data and therefore has first dibs on the data. And how do you balance the time release such that the collaboration can get access to what it wants to do without actually holding up what other people want to do? And we're starting to see a lot of requests come in to give us more of our, for us to give more of our data more quickly. And I think we're kind of tuning that. So it's an experiment that's in progress and we're evolving.
Thank you. Question from the audience? Right here.
Thank you again for sharing such remarkable stories in many aspects. You commented about CMS and Atlas competition. Certainly, we compete.
Right.
But I would say that there are a lot of collaboration between two experiments as well. Of course, we have a different philosophy in detector designing and doing analysis. But that's how we compete. But there are quite a bit of knowledge sharing for both scientific knowledge and technical knowledge. On top of that, our students, after degree, they go to join another experiments. Our postdocs going to the other experiment as a faculty. So it's really quite a bit of a collaboration between two experiments. So I want to point that out.
I apologize if I just insulted you.
No, it's okay.
Okay.
Hi, I'm just curious about if anyone has...
Could the questioners identify themselves?
Oh, hi, I'm Linnell. I'm a graduate student at Harvard. So I have a question. I'm curious about whether or not anyone has any idea about the approximate number of like interferometers that need to be built to like achieve some like, you know, appropriate amount of accuracy, and what the difference would be between like whether or not you have 2 interferometers versus like 10, and whether or not there's like some significant impact in like, I guess, adding more eyes. I'd kind of think about it that way.
Yeah, it's a very good question. It's like, where's diminishing returns come in? So 2 interferometers is definitely not enough. So the minimum you need is 3. However, because of the gravitational waves, if you ask yourself what's the best you can possibly do, all right, the best you can possibly do is given by the diffraction limit, and turns out that these gravitational waves are, Earth-sized, in terms of their wavelengths. So the Earth, in some sense, is the limiting aperture. So if you have 3 interferometers that are distributed as far apart as you can, that will give you good localization in some parts of the sky, very poor localization in other parts of the sky, particularly where you have hidden plane. So you really need a 4th one, all right? And so there's Kagra detectors, that 4th one. India, all right, which is coming online, in some sense gives us, I think, we're the best of all worlds, because the thing I didn't tell you is that these interferometers are very twitchy. They're not always online. So we're in a run right now where we're detecting a gravitational wave event once a week. All right, we see black holes merging every week. All right, the events that we detect are not always detected by all the interferometers. So you want a robust network so that you're sure that most of them are on. So 10 is too many. All right, 2 is probably too few.
Any other questions? Arthur?
The next generation will be very expensive.
Yes.
Arthur B. Noonstock, Stanford. The next generation detectors will be very expensive. Have you reached a consensus on what organizational structure you're going to use for that purpose?
No. And the reason is that these projects are sort of incubating nationally. There's a project, Einstein Telescope, that's incubating in Europe. There's a project in the United States that's actually further behind. I would say that Europe is actually ahead of us in terms of developing a roadmap to getting to that 3rd generation. Having said that, there are discussions taking place, and there's a real focus on trying to come up with a governance structure that will allow us to do something. So on the one hand, we have convened committees to look at this internally within our community. And they've made very strong recommendations, and these committees are global, they're not just from the US or Europe, that we should be looking towards the most unified management structure that we can have. You'll get better, it'll be easier and more efficient to build a detector. You can share, the resource allocation is easier and things like that. But as anybody who works in a big, large collaboration where you have different governments, it's a very complicated thing. So it's going to take us a while. The timescale for these detectors is probably in the 2030s. But that's not that far away. So we really are, thinking hard about that and trying to move in that direction.
So I have a question. Historically, you started with it looks like you started with the high energy physics detector culture.
Right.
Barry, of course, came from there. And then you have modified them. So do you have any lessons now for the high energy
That's an interesting and provocative question. So while I'm thinking about how to answer it, I'll start out by saying that actually there's even an evolution. The high energy culture that we adopted was sort of brought in by the management when Barry Barish took over. But before that, it was not at all. It was very much, I would say, small groups of people at MIT and Caltech and in Germany that were all working together. Well, I guess the person who asked the question over there, Young-Hee Kim, basically, I think, sort of said the right things, that cooperate where you can. All right. The difference between gravitational waves and particle detectors is we, in some sense, already built in experimental corroboration by having two different detectors see the same kinds of signals. So I would probably argue that they could teach us a thing or two about this sort of thing also.
Hi, student 3 from AAAS. I like your slide about Nobel Prizes are won in congressional hearing rooms. I'm one of those former bureaucrats. Talked about. What has been the reaction? Has the reaction in those congressional hearing rooms been as positive as the scientific reaction to the work you like?
I think so. A number of us testified in front of the House committee, not long, in fact, the month we made the announcements, and it was, in the words of the person that we work with in the government relations office, a love fest. They were very happy. Now, question is, does that translate into anything more substantive? That's a harder thing to measure. But one of my jobs is to go around and talk to congressional staffers and occasionally Congress people, and I get a very warm reception. I always say funding science in general, it's not just about LIGO and gravitational waves, is very, very important. So I think the answer is yes. Where it becomes more complicated is when you start talking about big international collaboration. So we were thinking about this idea of going to India back 2011, 2012. And I met with the staffers from the House Science, the minority staffers, and their comment, and it really ties into some of the one of the major themes of this conference is, we wouldn't even be having this meeting if you were coming to us saying you wanted to build this with China and in China. They said the only reason we're having this meeting is because India is a friend of the United States. So I think that's where you start to run into resistance.
Okay, we thank you very much. It was a wonderful talk.
Really great. Good.
And we now have a coffee break for half an hour. Plenty of time to discuss. We're going to continue with a panel discussion in half an hour.
Good.
I would like to ask members of the panel to get themselves mic'd in the back.
Talking about next generation LIGO.
Yeah.